So suppose I have a function, and here's a function, and suppose this is this noisy signal. I want a nice smooth version of it, right? So how might I do that? Well, we've learned before that you might blur it with, let's say, a Gaussian kernel. Okay, and what does it mean to blur it with a Gaussian kernel? We're going to convolve the underlying image with that Gaussian. But it turns out the Fourier transform of a Gaussian is a Gaussian. All right? And that's what this shows here. So the Fourier transform, if this is h of x, this is h of u, it's another Gaussian. But you'll notice that here it's over sigma squared, and here it's times sigma squared. Okay, and that's what this is trying to show you here, is that if I have this Gaussian kernel with a variance sigma squared, that I get a new Gaussian, and I apologize, this is an awfully drawn Gaussian. I get a Gaussian whose variance is 1 over sigma squared. Now, if you think about that, that makes a little bit of sense, right? First of all, let's think of a really, really skinny Gaussian, all right? Like almost an impulse. Remember when you convolve a function with an impulse, you get back the original function? So that means you basically keep all the frequencies. So if my kernel was a very tight little Gaussian, I would expect to be able to keep all the frequencies. I would expect to be able to get almost all of the frequencies back. Likewise, let's suppose my kernel was really, really fat, blurs the heck out of everything. Well, then I would expect to get hardly any high frequency and only to get only the low frequencies. And that's why the Fourier transform, that's one way of thinking about that. The Fourier transform of a fat Gaussian is a skinny one, and the Fourier transform of a skinny Gaussian is a fat one. Remember, they go back and forth. All right. So what's going to happen when we blur this function with the Gaussian is we're going to multiply its Fourier transform by the Fourier transform of that Gaussian. And what it's going to do is it's going to keep the low values and it's going to lower down the higher frequencies. It's going to reduce the higher frequencies by doing that multiplication. And we say that that means that it attenuates. That's the word we use. It attenuates the high frequencies. So I can show you an example of this being done in 2D, that is with an image, here. Okay? Here we have an original image, a beautiful little still life of some fruit in black and white. And here is its Fourier transform power spectrum, just the magnitude. So I'm not showing you the phases. The middle, remember we put the origin in the middle, is the low frequency. And you can see that it falls off as you get out to the outside. Now, we're going to blur this thing with a Gaussian. And I'm showing you this Gaussian here at the same scale as the whole image. So this Gaussian might be 15 by 15 pixels, but it looks really small because we have a good-sized image. But that would blur the image a little bit. And when I convolve the Gaussian with the original image, I get exactly what we'd expect, a slightly blurry version of the image. But look what happens in Fourier space. The Fourier transform of this tight little Gaussian is this big fat Gaussian. Remember we said small Gaussian in space has a big Gaussian in frequency. And then we multiply this times this, and what that's going to do is it's going to keep the areas in the middle, which you see here, but it's going to attenuate the areas on the outside. So it reduces those low frequencies. And in fact, if I had wanted to, in order to recover this image, what I could have done was taken the Fourier transform here, multiplied it by this one, gotten this, and recovered back. Except that to actually do the recovery, it wouldn't be enough to just look at the magnitude. I would actually have to keep the real and imaginary parts. I'd have to keep the phase of the transform. But here I just wanted to show you what happens to the different frequency power. We've actually looked at this just a little bit before when we introduced the notion of frequency. So here we have a picture of this, we did have this picture, this man-made scene, all right? And here what I did was I took the inside part and I set this all equal to 0. So instead of tapering it off like a nice Gaussian, I was ruthless and I set all of the frequencies outside a certain diameter to 0. So there's no high frequency component at all. And what you get is this ugly looking thing called ringing, all right? So this actually has low frequency, but because of some slight variations in here, it can't cancel them out with higher frequencies that it needs. Okay, so what gets left over is what's called ringing, and that's what happens when you clip the frequencies precisely. And I'm going to make that mathematically better defined in just a minute. The flip side of that is if I remove just those center frequencies, and I think in the image processing world this was called coring, where you pull out that center, all that you get left with is this high frequency bit, which is a lot like what? The edges. Okay, we know that there's this relationship between frequency and edges. At the high frequency is where you get these steep derivatives. All right. Let's continue looking at this relationship between the spatial domain and the frequency domain. Here are some simple properties of the Fourier transform. We started with one that we already talked about. Everything is linear because we're just doing sums and multiplies. All right. The one we just described was this convolution one, that convolution in the spatial domain is multiplication in the frequency domain, and vice versa. One that's kind of interesting is scaling. So if I scale a function by a constant a, so let's think about it this way. Suppose a was greater than 1. Let's suppose a was 2. All right? Well, that would mean that when x had been 1, now x is 2, so it would shrink, right? When you multiply by a number bigger than 1, right? So if I had some function, right, now what happens is this value gets moved over there, so I essentially shrink that function, okay? So when I shrink a function, things are going to now wiggle faster, right? Because they were wiggling slower before. If I pull it in, it now wiggles faster. And so what happens is I end up stretching the Fourier transform. And this is the formula for it, 1 over a times f of u over a. So it's got that inverse property, which is just like that Gaussian idea also, right? If I make it fatter, my Fourier transform gets skinnier. One last one to look at, and we're not going to use this much, but I wanted you to see this, is when you take the derivative of a function, so this is some nth derivative, you multiply its Fourier transform by a function that's proportional to the frequency. So suppose n was just 1, you're taking the first derivatives, right? What that says is that you would be multiplying f of u times u, which means the higher frequencies get accentuated, which was exactly what we saw when we took derivatives. Remember when we added noise, high frequency noise, and then we took the derivative, the whole thing blew up? That's because you were multiplying it by, when you take this derivative, you multiply the high frequency components. If you take a look at Rick Zalisky's book, which we mentioned earlier, you can see a whole bunch of Fourier transform pairs. For example, the impulse, which is drawn like that, has a Fourier transform of 1. As we said, that makes sense because the impulse, when you convolve it, just gives you back the original function, so it better keep all of the frequencies. Likewise, we said here that the Fourier transform of a Gaussian is another Gaussian, but again, g of sigma goes to 1 over sigma. So fat Gaussian in space, skinny Gaussian in frequency. But look at this one. If I have a box filter, which is just a filter that's shaped like a box, it produces what's called the sinc function. Okay, and that's drawn here. And let's look at that a little more closely. Okay, so here in the spatial domain, we have our box filter, and this is our sinc function. All right, now sinc of x is sine x over x. All right, and you can think about that if you take the limit as x goes to 0. Well, you remember L'Hopital's rule, take the derivative of the top, that's cosine. The derivative of the bottom is just 1. Plug in a 0, it's 1. So the limit as x goes to 0 is in fact 1 right there. And then as x gets bigger, the sign gets attenuated, and that's what you're seeing here. So in other words, if I were to convolve something with a box filter, my frequencies are going to behave kind of in a weird way. You know, have this nice kind of low pass stuff, but then I'm going to have these various other frequencies that are going to get accentuated. And if you remember, we did that very early on when we introduced filtering. Remember we convolved something with a box, with a square? And we said, man, is that ugly? This is why it's ugly. So you see this picture here? You see how it's got all these like striations? And I said, when we first did this, that that's because boxes aren't smooth and that we would make this more formal when we did Fourier analysis. Well, I made good on my promise, okay? The reason that when you convolve an image with that little square box that you see all this junk is because of this ringing here in the frequency domain. That's why we said what you should do is do what? Is you should apply a Gaussian, not a box. It makes a nice pretty picture, a nice smooth picture, because in the frequency domain you get this nice smooth Gaussian. One more thing about these sinc functions, okay? So we showed that the Fourier transform of a box is the sinc. Well, because of the symmetry, if I had a box in frequency space, that would be a sinc in the spatial domain. So what if I were to take some function, take its Fourier spectrum, and multiply it by that box? What would that look like? Well, I already just showed you that, right? This is essentially, it's sometimes called a pill box because it's a box but in 2D. That is, instead of being just a particular width, it's a radius, right? So everything outside that diameter is set to 0 and everything inside is kept exactly. If you remember, the picture we got was this ugly picture with all this ringing in it. Well, now we know why. When you multiply the frequency by a box, it's as if you convolved the image with its Fourier pair over here with the sinc function. So if you take this pretty picture and you convolve it with this ugly beast, you get something that looks like that. And that's where the ringing comes from. That's why you never want to just cut out the high frequencies, because what you're essentially doing is convolving your image with a sinc function. That ends this lesson on the relationship between convolution in the spatial domain and the frequency domain. In particular, the convolution in the spatial domain is multiplication in the frequency domain. We've also made good on the promise of explaining some of these ugly artifacts that we saw. In particular, ringing is sort of the Fourier transform of a box. That is, if you cut off the frequencies hard, you get this ringing, or if you have a cutoff in space that's hard, you get this ringing in frequency. What we now have are the tools that will allow us to tackle aliasing. That is, when you do something to an image that involves sampling that causes it to look really ugly, and high frequency stuff. It's a little bit of a bumpy ride, so strap yourself in and get ready for the next lesson. All right, welcome back to Computer Vision. This is going to be our last lecture or lesson or whatever this is on frequency analysis, and I bet you're happy about that because it's kind of off in the ozone of mathematics, and it's going to be hard to pull it back to the work that we'll be doing in terms of manipulating the images, but it's important. And in fact, today we'll finally get to the coup de grace, pièce de résistance. My French is terrible. What I really wanted to get to was the notion of how frequency explains the notion of aliasing. So if you remember, we've been talking about Fourier basis sets where we decompose things in terms of sinusoidal bases, and this is the picture we've been using to represent that. And then we talked about the relationship between convolution in the spatial domain giving you multiplication in the frequency domain. And we showed it with the math here. We said that if G was the convolution of some functions f and h, that we could derive that convolution in the spatial domain was multiplication in the frequency domain, and that was shown like this. And by the way, then this is really important for today, that multiplication in the spatial domain is convolution in the frequency domain. And you might ask, when do we ever multiply functions together?
When do we ever multiply functions together?
Today. It'll be some very special functions, but we'll do that today. We also showed some Fourier pairs. We talked about how the Fourier of a Gaussian is another Gaussian. We talked about an impulse is straight. We spoke about the box filter giving you this sinc thing that explained ringing and that like. But there's one other pair that I need you to know about. And again, we're not going to derive this, but it's important. And that is the notion of a pulse train or a set of impulses, okay? And so this is referred to as a pulse train. You can see that here. And the Fourier transform of a pulse train is another impulse train. And the thing that you need to realize is that, and remember the scaling theorem gives us this and a bunch of things give us this, right? As the pulses in space get further apart, the pulses in frequency get closer together. And this is a hand-wavy way of thinking about this. Imagine that our pulses got very, very far apart, okay? So far apart that I have an impulse in the middle and the next one is infinitely far away. Well, that would be just like having sort of a single impulse. That's the hand-wavy part. Well, what is the Fourier transform of a single impulse? Well, we said it was a 1 because an impulse gives you back when you convolve it, it gives you back the entire image. So therefore, the frequency has to keep all